Hello and welcome to my presentation. My name is Seyed Mohammad Mojtabaei, and the collaborators of this project were Dr. Iman Hajirasouliha from University of Sheffield and Dr. Jurgen Becque from University of Cambridge. The title of this presentation is Optimized Design of Cold Form Steel Elements for Serviceability and Ultimate Limit States. As you know, cold form steel sections has got flexibility in shape, and they can be manufactured in different cross-sectional shapes. The aim of this project is to basically develop a practical framework for the optimized cold form steel beam sections with the maximum flexural strength and minimum deflection in ultimate and serviceability limit state conditions, respectively. And the methodology that we have used in this study is as follows. A population-based genetic algorithm optimization method was employed to obtain optimum solutions for 10 different cross-sections prototype. And also, Eurocode-3 effective width method is used to determine the stiffness and strength of the cross-sections. And at the end, Eurocode-3 geometric restrictions and a number of manufacturing and end-use constraints were imposed to the cross-sections using the optimization. Eurocode 3 actually was used for to basically calculate the design resistance of the cross section. Actually, Eurocode 3 for local buckling prescribed that the corner zones of the cross section play an important role in carrying the load capacity. And as you can see in this figure, the effective width of the lead channel section is shown, and Eurocode 3 basically says that the shift of the centroid of the effective cross section relative to the original centroid, which is called En, should be taken into account during calculation. And also the stress distribution and the effective width of the internal compression element and outstand compression element was basically recommended by the Eurocode, and an equation was proposed by Eurocode to calculate the effective width. Design resistance of the cross section for distortional buckling, also proposed by Eurocode. Actually, distortional buckling involves a distortion of the cross section with translations occurring at interior fault lines, and unlike what Eurocode 3 prescribed for the local buckling, here in Eurocode accounts for distortional buckling through reducing the effective plate thickness, and the slenderness for against distortional buckling, lambda d, is a function of material yield stress, and sigma CRS, which is elastic distortional buckling stress. This elastic distortional buckling stress is calculated by assuming the fact that by assuming a simplified model of the sub-assembly in isolation, where the restraining effect of the adjacent plate is simulated by elastic springs, as you can see in the picture proposed by Eurocode. For the global buckling, we use Eurocode 3 part 1.1, and global buckling resistance of the cold form steel beam is calculated by using this equation. MBRD is equal to XLT W effective F phi over lambda M1, which is X. In this equation, XLT is the reduction factor for lateral torsional buckling, which depends on the global buckling slenderness, lambda LT. W effective is the effective section modulus, and Fy is the material yield stress, and lambda M1 is basically safety factor, which is taken equal to 1. And global slenderness is determined based on the elastic critical moment of the beam, which is called M critical. Okay, now let's define the optimization problem. The optimization process aims to maximize the bending moment capacity and stiffness of the cold form steel beam cross sections in this study. The starting point of the optimization was basically taken as a standard commercial section, and this commercial section, as you can see in the picture, will be used to assess the effectiveness of the proposed optimization process. During the optimization, we consider that the rounded corner radius is always 3 millimeter. the total amount of material used was kept constant in the optimization process. Coil width of the steel was taken equal to 453 millimeter, and plate thickness was taken equal to 1.8 millimeter. And for the material properties, elastic modulus is taken equal to 210 gigapascal, and yield stress equal to 450 megapascal, and Poisson ratio equal to 0.3 value. And 10 different prototypes were selected, and as you can see, we try to have unlipped section or plain section, and also consider the effect, basically the lips, the lip channel, and also double folded lips, and intermediate web stiffener, and also folded channel, which is a newly developed channel, and it was developed at the University of Sheffield. Each prototype was individually optimized during, using the two different optimization targets. The first one was ultimate limit state, or ULS, and the second one serviceability limit state, or SLS. And Eurocode 3 design constraints, as well as the practical and manufacturing limitations, were imposed on each cross-section type. For example, minimum dimensions required for manufacturing was applied. It means a minimum lip length of 10 millimeter was taken into account, and also minimum dimensions required for the construction practice was considered. For example, a minimum flange width of 15 millimeter was used to establish the connections between the cold form steel beam and other elements, such as trapezoidal decking, plywood boards, and angle plates. And as you can see in the table, all Eurocode 3 design constraint and manufacturing limitation, which was obtained from from consultation with the industrial collaborator of this project, and it was proposed for all of these selected cross sections. The optimization procedure was conducted using two distinct pieces of software in MATLAB, a program implementing the Eurocode 3 design rules, and also a program carrying out the GA optimization. To ensure that the optimum results were consistent, each of the prototype was optimized 3 times using randomly selected initial values for these variables. And as you can see, the differences, for example, for one of the cross sections, the differences between the 3 rounds was always less than 1%, which means that there is a consistency between the maximum predictions. Okay, the optimization targets in this study, as we already mentioned, were ultimate limit state and serviceability limit state. For the ultimate limit state, we try to maximize the capacity of the beam element, the maximum capacity of the beam element, and in this function, X is the basically design variables, and XIL and X, which is always between XIL and XIU. XIL is the lower bound of the lower bound value of the design variable, and XIU is the upper bound value of the design variable. And for the serviceability limit state, the target is actually the deflection of a simply supported beam under external bending moment at 2 ends. We consider that the L is the length of the beam and is taken equal to 5 meter. FIC is the effective second moment of area, which is proposed by Eurocode 3 part 1-3. And IGR is second moment of area of the gross cross section. Sigma GR is the maximum compressive bending stress at serviceability limit state based on the gross cross section I sigma effective is the second moment of area of the effective cross section calculated for a maximum stress, and sigma gr and sigma can be calculated using the fundamentals of the structural analysis. Okay, uh, for the MED, MED at the serviceability limit state, it means the applied bending moment at the serviceability limit state. We consider that this ratio, the ratio of the applied bending at the serviceability limit state over the flexural capacity of the cross section equal to 0.7. This value is actually equal to the ratio of the average partial safety factor for the serviceability limit state over the one for the ultimate limit state. And the optimization results at ultimate limit state are listed in this figure. Actually, all the dimensions for each prototype are listed in this figure. As you can see in the results, and by comparing the M max, the capacity of the cross section, over the M max standard, which is the capacity of the cross section for the the capacity of the standard cross section, we can conclude that proposed optimization method was able to significantly increase the bending moment of the standard cross section by up to 55% for prototype 10, which is the folded flange section. So using folded flange section can increase the capacity by 55% compared to the standard cross section. Also, optimized cross section tend to adopt, actually as a general trend, optimized cross section tend to adopt a deeper web and consequently narrower flanges. In addition, bending moment capacity of the benchmark lip channel was increased by 30% by only optimizing its relative cross-sectional dimensions. It means prototype 4. In addition, by adding basically double fold edge stiffeners or double lip, an additional 10% higher flexural capacity was obtained. It means if you have a look at the prototype 7, you can see the effects of double fold edge stiffener. Plain channel section or prototypes 1, 2, 3 did not lead to very efficient design solution even after optimization. As you can see, M max and M max standards for these cross sections are very close to 1, but for cross section 1 and 2 is even less than 1 compared to the standard cross section. In addition, flexural capacities of the optimum lip channels prototype 4 and 7 were not generally enhanced by incorporating intermediate stiffener in the web. At serviceability limit state, similar to the optimization for ultimate limit state, the optimized cross section tend to display a deeper web and narrower flanges. In addition, by simply optimizing the relative dimensions of the standard benchmark section at serviceability limit state, the flexural stiffness and capacity of the section can be increased by 37% and 11% respectively. Dimensions of the optimum plane channels prototype 1, 2, and 3 for the serviceability limit states are very similar to those obtained for ultimate limit state. In addition, optimum plane channels perform quite well at the serviceability limit state, considering outperforming the benchmark lip channel and providing a substantially higher effective stiffness, up to 44% higher. Introducing intermediate stiffeners in the web generally reduce the flexural stiffness of the optimum sections at the serviceability limit state, as is apparent from comparing prototypes 2 and 3 to 1, 5, 6, and 4. For folded flange section, prototype 10, a noticeable increase up to 54% in both effective stiffness and capacity was obtained over the standard cross section. Thank you very much.